So, we are starting a new paper, May-June 2022, paper 5-2. Let's start with question number 1. A student plans an experiment to find a value of the molar volume Vm of hydrogen gas at room conditions. So we know that the molar volume of any gas is actually 24 dm cube, but in this experiment is designed to actually find out the value whether we are getting exactly the 24 decimeter cube or the smaller or the greater than that. Hydrogen gas is formed when magnesium reacts with dilute hydrochloric acid, and here they have provided you the chemical equation for this reaction. The student is provided with the following materials. Okay, and these material contains a piece of a magnesium ribbon, 0.5 mole per dm cube hydrochloric acid, a water trough, a side arm conical flask, a 250 centimeter cube measuring cylinder with a 2 centimeter cube graduation for the collection of a gas. So it means that it have a scale or the units per each 2 centimeter cube, a 50 centimeter cube of a measuring cylinder, a balance that measures to a 2 decimal places, and access to any necessary lab equipment except gas syringes. So you have to keep in mind you don't use gas syringes. Okay. Now, the student plans the following procedure. Okay, remember in this designing part, whatever the question is or whatever the method is, they always give you a method in which there is some part is missing and some part, there is some error in the method, and after describing the method, they always ask you about that. Okay. Now, in step 1, prepare a piece of magnesium ribbon for use in the experiment. Okay. What would be the preparation? Because these are relatively reactive metals, so their surface must be reacted with the oxygen to form the oxide. So we use a sandpaper to scratch the surface so the shiny metal come outside instead of the oxide layer. So that's what the preparation is. In step 2, measure 30 centimeter cube of a hydrochloric acid and pour into a side-arm conical flask. And if I recall, yeah, here it is. Its concentration is also provided that hydrochloric acid is 0.50 mole per dm cube. Attach the conical flask to a collection system for the hydrogen gas. Place a magnesium ribbon in the conical flask. Stopper the flask. Okay. Wait until the final volume of gas collected is constant. Wait for additional 2 minutes, then measure and record the final volume of a gas collected. Okay. Now, in A part, they are asking to complete the figure 1.1 to show how the apparatus should be assembled for the collection and the measurement of gas. Label your diagram. Okay. So as the water trough is provided and hydrogen is basically, water insoluble. So the gases which are normally water insoluble are collected using water displacement method. So here you are observing the side arm flask, right? Now you have to draw the diagram. Just give me a minute, please. Okay. Now, what we will do, we will make one or show one delivery tube. like this. Here we would make a water trough. It is filled with water. And here on some stand, we will keep a measure cylinder over here. Where it is a measuring cylinder of 2 centimeter cube graduation. So we would put this cylinder over here. Okay. Yes, is this clear to everyone? Yes. Yes, sir. Okay. And do show some water over here and show the bubbles that hydrogen is basically displacing the water from the top. Okay. Now, in B part, the surface of the magnesium ribbon has an oxide layer. State how the student should prepare the piece of the magnesium ribbon before it is used in this experiment. So see, that's what I have discussed with you earlier. So what we can write, use sandpaper to remove the layer of its oxide. Okay. Now, state what additional information about the magnesium is required before the experiment is performed. So see, that something is missed. So can anybody recall and tell me what additional information that is needed? Look at the method over here. So can anybody identify?
Mass of magnesium.
Yeah, very good. The mass of magnesium is needed because if we are going to identify the hydrogen gas, that how much moles or the volume is produced, so we have to relate them, and for that we need the mass of magnesium, that how much magnesium is being used in the experiment. So here, mass of magnesium. Now, show by calculation that a volume of 30 centimeter cube of 0.5 mole per dm cube is enough to react with 0.16 gram magnesium ribbon. Show your working. Okay. So that we have to show that these two must be in the ratio of 1:2 as they are provided in the equation. Okay. So let's find the moles of both the substances. Moles of hydrochloric acid would be equal to its volume times its concentration, and as the volume is in centimeter cube, so I have to divide it by 1000 to turn into decimeter cube. So can anybody tell me the answer, please? Yes. 0.15. 0.15. Can you do it again? Sorry, sir, 0.015. 0.015 are the moles of magnesium. Sorry, hydrochloric acid. Now, moles of magnesium. And to find the moles of magnesium, divide its mass with the AR of magnesium. And if you look at the AR of the magnesium provided in the periodic table at the end over here, it's 24 point, right? So 0.16 divided by 24.3 would give me the moles of magnesium. Yes, can anybody tell me the answer, please?
Zero point 00658.
0.00658. These are the moles of magnesium. Okay, so we have to take the ratio of these moles to find whether they are existing in the 1:2 ratio or not. So one for 1 mole of magnesium, 2 moles of hydrochloric acid is required. That is provided. No, 1 minute. Sorry. So here the moles of the magnesium are 0.00658, and for that moles of magnesium, the hydrochloric acid available is 0.015. So if we need a 1 mole of magnesium, for that 1 mole of a magnesium, how much hydrochloric acid is used? So here, find the value of x. So x would be equal to 1 into 0.05 divided by 0.00658. Can anybody tell me the answer, please?
2.28.
2.279.
2.28.
2.28 moles. Okay. So see, the x is 2.28 moles. So for 1 mole of a magnesium, we have 2.28 moles of hydrochloric acid, which is actually greater than this, right? Is this understandable to everyone? So we can say that 0.16 gram of magnesium is enough to react with 0.16 gram magnesium is enough to react with its enough to react. That's what they have asked in the question. Now let's move to the next part. State why it is not necessary to use a burette to measure 30 centimeter cube of 0.5 mole per dm cube HCl. So from the above question, sorry, it's mole. No, yeah, it's gram. Sorry, my bad. So from the above part, we already known that hydrochloric acid is in excess, right? So it doesn't matter, or does it matter whether its volume that is measured is accurate or not? Because burette is needed for the accurate reading, and if we are using any other measurement apparatus that is like, for example, measuring cylinder, so it would be, approximate. It is actually for the approximate measurement. So here hydrochloric is in excess, right? So it means yes, it is not necessary to use burette, because HCl is in excess. So it doesn't matter whether it's a accurate value or accurate volume is measured or not. Is this clear to everyone?
Yes, sir.
Okay. Then the student waits for 2 minutes before taking a reading of the volume. Suggest why the student waits for 2 minutes before measuring the volume of gas in step 7. Yes.
ताकि सर पूरा सॉल्यूशन जो सैचुरेटेड हो जाए.
No. It is a reaction between an acid and a metal. So what would happen during this reaction? The energy is released. So if the energy is released, the temperature is raised, and we have to find the molar volume, right? So to find the molar volume, we actually have waited. The student actually have waited. So this temperature uh, again lowers down to the room temperature. So we can measure the volume of the gas or record the volume of the gas at a room temperature, because we have to find the volume of a 1 mole of a gas at room temperature, right? So here we would write that it is to make sure that the temperature of gas lowers to room temperature. Is this understandable to everyone?
सर हम ये लिख सकते हैं कि जब तक गैस का टेम्परेचर जो है चेंज करना बंद नहीं होता, मतलब जब कांस्टेंट हो जाता है।
We are not using thermometer, so we can't write that. See?
ठीक है सर।
Yeah, but here they have mentioned that access to any necessary laboratory equipments except gas syringe. So yes, you can write that the temperature must be reached to room temperature. Okay. Now, E part, the student collects 146 centimeter cube of hydrogen gas during the experiment. Calculate the percentage error in collecting the hydrogen gas. Show your working. So, if you look at the list of the apparatuses again, here it is. For the collection of gas, the measuring cylinder that we have used is 2 centimeter cube, have a scale of a 2 centimeter cube. So it is its least count, right? And the uncertainty would be identified dividing the least count by 2. So 2 divided by 2 gives you 1. So the uncertainty in the reading would be 1 centimeter cube plus minus, right? So the percentage error would be 1 divided by 146 times 100, because when you are recording the volume, we are not taking the two readings, we are just taking the one reading. When the reaction is finished, we just note down how much volume is decreased, or how much volume of a gas is collected. So that's why we would just take the least count divided by, the uncertainty divided by the total volume and times it 100. Can anybody tell me the answer, please? Yes.
0.685.
0.685%. So 0.685%. Okay. Now, next part. Calculate the molar volume of hydrogen gas using the student's result from this experiment. Okay. So, we got the volume and if you see over here in the equation that the moles of magnesium and the moles of hydrogen are same, right? And the moles of magnesium that is used in this experiment is 0.0068, and hence it's a limiting reactant because it is going to be consumed completely because it is in the lesser amount. So the moles of magnesium are 0.00658, and if we take the ratio between magnesium and hydrogen, we have seen in the equation it is 1:1, right? So for 0.00658 moles of magnesium, the hydrogen's moles are X, and X is exactly equals to 0.00658. So these are the moles, and these moles are actually occupying 146 centimeter cube of volume. So if there is a 1 mole of a hydrogen gas, this is the moles of the hydrogen gas, and this is the volume of the hydrogen gas. So then how much would be the volume. It is equals to X. So can anybody find this X, please? It would be found by 1 multiplied by 146 divided by 0.00658. Yes, can anyone tell me the answer, please?
Sir, 22,200.
Is it 22,200 only?
नहीं sir, round off किया है.
Why? Tell the
Sir,
correct value.
22,188.45.
188. Okay. So 28,188 centimeter cube. Is this clear to everyone? Now, F part. The student's experimental value for the molar volume of hydrogen is lower than the value quoted in the table of the important tables, constant at standards on page number 11. If you see over there, you will find that it is 24 dm cube, right? So at room conditions, it's 24 dm cube, and at STP it is 22.4. But for this, we will be using this value at room temperature. So here they have provided 24.0 decimeter cube at room temperature pressure. Okay. Suggest one experimental weakness that might have led to this outcome. Okay. So it means there must be an error in the method. Or there is a one weakness in the methods. Explain how method could be improved to overcome the weakness you have noted. Yes, can anybody tell me the weakness? Here you have the whole method. Yes, can anyone identify what is the weakness, why we are getting the lower value?
Because gas is safe
Sorry, can you
safe
repeat?
when you're putting the stopper on.
Yeah, good. When we drop this magnesium ribbon down and then we put this stopper, so there is a chance that before it is being airtight, some of the gas would escape. So we can write that some of the gas may escape. Now, how would we improve this? So the improvement would be that we make sure that the reagents didn't mix or stay separated until it is sealed. So the improvement would be make sure that both the reagents stay separated until flask is sealed. Is this clear to everyone? Yes. Okay, now we are done with question number 1. Now we are going to start question number 2. In a neutral solution, aqueous potassium iodide acts as a catalyst for the decomposition of aqueous hydrogen peroxide. So it means in this reaction that potassium iodide is behaving as a catalyst for this reaction. A student plans to carry out an investigation to find out how temperature affects the initial rate of the decomposition of aqueous hydrogen peroxide in the presence of aqueous potassium iodide. Okay, so we have to find the effect on the initial rate, and that effect is by changing the temperature. The student knows the initial rate of the reaction can be measured by timing the production of the oxygen. Okay, so we would record the amount of oxygen produced in equal intervals of time. The student carries out a series of experiments. Okay. In experiment 1, the student notes the temperature of the H2O2 and aqueous potassium iodide under room conditions. The solution are mixed in the apparatus designed to collect the oxygen gas produced. A stopwatch is started at the beginning of the reaction. The volume of the oxygen is noted at regular time intervals. Okay. In experiment 2 to 8, the solution are heated to different temperatures before mixing and measurements of the oxygen produced. So in each experiment, we have used different temperature. The data collected is used to determine the value of activation energy for the decomposition of H2O2 in the presence of potassium iodide. Okay, and from that data, we will also calculate the activation energy. We will identify the determine the activation energy. State the independent variable. Yes. What is the independent variable? Remember, the independent variable is the one which we are controlling on our own. So what we are doing, we are performing. Sorry. Temperature, very good. So we are doing the reaction at different temperatures, right? So it means that temperature is the independent variable for this experiment. Now, next part, state 2 variables that needed to be controlled. So we are using 2 different, reagents, and both are aqueous. One is a catalyst and one is our reactant, a reagent hydrogen peroxide. So we must take care that the volume and concentration of H2O2 must not be changed, because if it change, it also affect the rate, right? In the same way, volume and concentration of potassium iodide must not be changed, because if we use the more concentrated potassium iodide, it would further enhance the rate of the reaction. So these 2 variables must be controlled in order to observe the effect of the temperature on the rate. Is this clear?
Yes, sir.
Now, next part. State how the student should prepare 250 centimeter cube of 0.1 mole per dm cube H2O2 from 0.5 mole per dm cube of H2O2. See, in the previous question, we have find this dilution one, that this is the concentrated or the stock solution, and we have to make this diluted solution, and in this volume capacity. Calculate the minimum volume of 0.5 mole per dm cube hydrogen peroxide required for the preparation of 0.1 mole per dm cube. Okay, so we have to show the calculation. Give the name and the capacity of any key apparatus which should be used. Okay, so first identify how much volume we have needed of 0.1 mole per dm cube hydrogen peroxide to prepare 0.5 mole per dm cube hydrogen peroxide. So we have this expression that C1V1 is equals to C2V2, or instead you can write concentration of a concentrated solution time volume of a concentrated solution is equals to concentration of a dilute solution times concentration of a volume of a dilute solution. So we know the concentration of a concentrated solution, which is 0.1. We don't know its volume, so let's make it X. The concentration of a diluted solution that we have to prepare is 0.5, and the volume is 250 centimeter cube. So if I'll find the value of X, it would be 0.5 times 250 over 0.1. So can anybody tell me the answer? Yes.
So 1250.
So shouldn't it be like 0.1 into 250?
We have to prepare 250 centimeter cube. Okay, yeah, sorry. This is the more concentrated one, and this one, no. Sorry, I have mentioned here wrong. This is the concentrated one, and this is the dilute one. So its value is smaller, right? So 0.5 times 0.1. So it would be 0.1, and here 0.5. Yes.
X is 50.
50. So it means 50 centimeter cube of 0.5 mole per dm cube hydrochloric acid is needed. Okay. So we have found the volume of hydrochloric acid. So we got the answer. Now transfer, we have to outline the method as well. 50 centimeter cube of 0.5 mole per dm cube H2O2 into volumetric flask using burette okay, 1 minute, into volumetric flask of 250 centimeter cube, right? Because they have given us the volume of the volumetric flask, the capacity that we needed to that we have to use. So and we would transfer it by using burette. Then fill the flask up to the mark with distilled water. Is this clear to everyone?
Yes, sir.
Now part 2. Hydrogen peroxide causes eye and skin irritation. State what precautions should be taken when preparing the solution in C1 other than the wearing goggles.
So gloves पहन ले.
Yeah, but always write when there is a skin irritation and you have to write that the student must wear gloves. So you must write that chemically resistant gloves, okay? For skin. Now, next part. The student performs experiment 1 to 8 using a range of temperatures. The results are shown in table 2.1. So here they have here are the temperatures at which the experiment is performed and the rates as well. Complete the table and record the values of 1 over T to 3 significant figures and the values of log initial rate to 3 significant figures. Okay. So can anybody going to tell me the values of 1 over t, and that is in Kelvin. So we have to take 1 divided by 293, 1 divided by 298. Yes, please tell me the values.
0.00341.
0.00341. Next value, please.
0.00336.
0.00336. Next value.
0.00330.
0.00330. Okay. Next one.
0.00325.
325. Yes.
321.
Okay.
313.
Okay.
308.
Okay.
305.
305. Now in the next we have to take the log initial rate. So we have to take the log of these values. Yes, can anyone tell me these values as well?
Negative 5.24.
Okay.
Negative 5.10.
Okay.
Negative 4.93.
Okay.
Negative 4.84.
Negative 4.84.
Negative 4.66.
Negative 4.66. Okay.
Negative 4.43.
Okay.
Negative 4.28.
Okay.
Negative 4.20.
Negative 4.20. Okay. Thank you, Hamna. Now, plot a graph on the grid to show the relationship between log initial rate and 1 over t. Use cross to plot each data point. Draw a line of best fit. Okay. So let's draw the graph. It's minus 5.24 and 0.341. Okay, let me do this. Minus 5.24 and 0.341. So 341 would be this point, and 5.24 here it's 5.2, and 5.24 must be over here. Then the next one is minus 5.10 and 0.336. So 0.336 would be over here, and it's 5.10, which is this point. Then The next is 330 and 4.93. 330 and 4.93. So 4.93 would be that one, right? Yeah. Then we have 4.325 and 4.84. 325 and 4.84. So 4.84 would be this point. And then we have 321 and 4.66. 321 and 4.66. So here it's 4.6 and 4.66 would be over here. Then three two five and 4.84. One minute. Okay, that's done. So 321, 313 and 4.43. 313. 313 must be over here, and 4.43. So here it is 4.4 and 4.43 would be over here. And then 308 and 4.28. 308 would be this one, and 4.28. So 4.28 would be this one. Okay, I think I did some mistake over here. 4.43 would be over here, not here. And then we have 4.66. Yeah, it must be here, not here. And 4.84 would be over here because it's in minus, so 4.93 would be over here. And then 5.1 and 5.24. So 5.24. Okay. So, and 305 and 4.20. So it must be over here. Now, you have to draw the line of best fit. So the line of best fit would be this is our line of best fit. Okay. Now what they are saying, circle the point on the graph you consider to be most anomalous. So if you see the most anomalous, there are 3 anomalous points, but the most anomalous would be this one, right? This one is the most anomalous point. Now, what they are saying, suggest one reason why this anomaly may have occurred during the experimental procedure. So here it is a rate, and rate is actually being calculated. So it's not the part of the experimental procedure, but the temperature must be at the experimental procedure. So instead, this point, 1 minute, this point is being over here. It must be being over here, which is indicating that we have, because it's a reciprocal, so basically the temperature we have recorded is higher than the actual temperature. The actual temperature would be lower. So here I will write that the actual temperature is lower and the temperature recorded is higher. Okay. Now, determine the gradient of your line of best fit. State the coordinates of both points you used in your calculation. These must be selected from your line of best fit. Give the gradient to 3 significant figures. Okay, let's find the gradient. We can use this point, that is 0.493 and 0.00330. The second point that we can take from this line is, okay, let's take this point. It is on y-axis 0.00335 and on x-axis it is minus 0.507. So we have took the values minus 0.493 and 0.00330 and minus 0.507 and 0.00335. So if we have to find the gradient, that is 1 minute, sorry, minus 0.507 minus 4.93 over 0.00330, sorry, 335 minus 0.00330. Can anybody tell me the answer, please? Yes.
Negative 280.
Negative 280. Okay. Now, the relationship between log initial rate and 1 over t is given by this expression. Okay, here we have a constant. Use the gradient calculated in D4 to calculate the value of activation energy. If you were unable to calculate, okay, we have calculated the value. So if you recall in the previous one that EA over R is basically equals to gradient. So here in this case, that we have this 2.303 as well. So EA over 2.303 R is actually equals to gradient.
Sir,
Yes,
sir, in gradient, house is like value negative 0.493.
493.
So like the x value,
Which one? Can you repeat again?
so like the first one, like why is it like 0.493 instead of 4.93?
Okay. Yeah, I didn't take the values. Calculation again. It is minus 5.70 minus 4.93. Sorry. It's not 0, it's 4.93 and it's 5.07. Yes. Can you tell me the gradient again?
Negative 2800.
Negative 3800.
2800.
2800.
Yes.
Okay. Negative 2800 is the gradient. Okay. So okay, here there is a minus sign. Negative E over 2.303 R is actually equals to gradient. So if I have to find the activation energy, it would be equals to minus 2.303 and R would be 8.31 times negative 2800. Yes, can anybody solve and tell me the answer, please? Yes, answer please.
53,586.
63,586
50,000.
joules per mole. Okay, so that is the activation energy to 53. Yes, is it 63 or 53? Okay, 53,586. Now, the last part, it is not possible to repeat the investigation, okay? State whether the data from the investigation is reliable, justify your answer. So if you see the data over here, we are getting the anomalous point. So if there are anomalous points, so we can't rely on this data. So we can say, no, it is not reliable because there are anomalous points on graph. Is this clear to everyone? Yes. So we have completed summer 2022 paper 5.2. Now tomorrow, inshallah, we will be attempting winter 2022 paper 5.2, and then we will inshallah attempt a February March paper as well. Okay. So see you everyone tomorrow. Take care. Allah Hafiz.